the second derivative. So recall that the second derivative is the derivative of the first derivative, which we write as f double prime of x, or d squared y over dx squared if we're using Leibniz notation. Turns out that the formulas can be used the same way to find the second derivative as we use to find the first derivative, which means that if we have the first derivative of a function, we can apply the formulas again to find the second derivative. So the power rule will work on a first derivative as well. It also works for all subsequent derivatives, third derivatives, fourth derivatives, fifth derivatives, if you ever needed to find those. So let's practice computing first and second derivatives together. Example 5. For each of the following functions, compute the first and second derivative. So we're going to start with the function 6 minus 3 over x plus 3 over x squared plus x to the 1/3. So again, we have to start with a rewrite because we can't really do anything when our variable is down in the denominator. So we rewrite this as 6 minus 3x to the negative 1. So here, remember that there's an invisible little 1 here that we don't usually write. So if we want to bring that up, we have to make that 1 negative. Similarly, 3 over x squared becomes 3x to the negative 2. And then our x to the 1/3 stays the same. So now we can use that to find the first derivative. So again, we're going to go term by term. The derivative of 6 is going to be 0 because it's a constant. For the next term, the negative 1 is going to come down to multiply the minus 3, giving me positive 3x to the negative 2. Now for the next term, instead of plus, I noticed that my power was negative, and so when it multiplies that, I'm going to end up with minus 6x to the negative 3 plus 1/3 x to the negative 2/3. So that was my power rule that I'm using to find the first derivative. If I want to find the second derivative of this function, I'm going to take the derivative of the first derivative. So again, I'm going to go term by term. So the negative 2 will come down to multiply the 3, giving me negative 6x to the negative 3, because again, I'm subtracting 1 from the power. The negative 3 is going to come down and it's going to multiply the negative 6. So I'm going to get plus 18x now to the negative 4 because I subtracted 1 from the power. And then here, I'm going to have a minus 2/3 times a positive 1/3. So that's going to give me minus 2/9 x. So 2/3 times 1/3 gives me the 2/9. You multiply the numerators and the denominators. And then negative 2/3 minus 1 is going to give me negative 5/3. So we use the same process on the first derivative to get the second derivative. Let's try it for the other examples. Part B looks a little funny. So for B, we have x to the e. Now remember that e by itself is a number, like pi. So when we have x to the e, it's still x raised to a number. So we can still use our power rule here. So when we find the first derivative, our formula says that the number in the power is going to come down and we're going to subtract 1 from the power. So we can write this as e times x to the e minus 1. It looks a little goofy, but it still works and it still follows all our rules. To find the second derivative, we're going to take the derivative of the first derivative, which means that this e minus 1 is going to come down in front. So we have e times e minus 1. And now if we subtract another 1 from the power, we get x to the e minus 2. Now this one, like I said, it looks a little goofy, but if you can follow along and apply the rules when you know it's a number, you'll be in good shape for this type of problem. Part C. So we have 6x to the 7th minus 20 square roots of x. Again, we want to get rid of that square root so that we can actually have a number to work with. So we rewrite the last term as 20x to the 1/2 power. So now, when we want to find our first derivative, we're going to go term by term. So the derivative of 6x to the 7th is going to give me 42. 7 times 6 is 42. X to the 6th. And then our second term here, we have half times 20. Half of 20 is 10. X to the negative half. So that's our first derivative. Our second derivative, we're going to take the derivative of the first derivative. So the 6 is going to come down and multiply the 42, and that's going to give me 252 x, and now we're going to subtract 1 from the power, so to the 5th. And then our second term, we have a negative half that's going to multiply a negative 10, so that's going to give me plus 5x. Now negative half minus 1 is negative 3/2. So we get 252x to the 5th plus 5x to the negative 3/2 as our second derivative. Example 6. Consider the function f of x equals 1/3 x cubed minus 2x squared plus 3x plus 1. There's a lot of things we want to do with this function, and what's really important here is that we need to remember, even though we have these formulas to compute derivatives, we are still able to discuss all the same properties of approximation in terms of the relationship between the original function and the first derivative, things like increasing, decreasing. All of those relationships still exist, even though we now have a better way of computing the derivative. So let's see how this all works out when we relate what we were doing before to what we know now. So first, let's compute the first derivative. So again, the 3 will come down to multiply the 1/3. That's going to give you 1 x, and we subtract 1 from the power to give me x squared, minus 2 times 2 is 4x to the 1, plus the derivative of 3x is just 3, and the derivative of 1 is going to be 0 because 1 is a constant. So that means that my first derivative is x squared minus 4x plus 3. We want to find the values for which the first derivative equals 0. So remember, your first derivative is going to equal 0 when the original function is constant. That's where we have those horizontal tangent lines. So if we set our function equal to 0, we're going to want to factor this to find the roots. So we'll get x minus 3 times x minus 1 equals 0. So that means we're going to have the roots x equals 3 and x equals 1. So these are the two values that's going to be when the first derivative equals 0. So we want to know when is the original function increasing and when is it decreasing. We said it's going to be increasing if the first derivative is positive, and it's going to be decreasing if the first derivative is negative. So if we were to draw a number line here, and we were to put on the values where it's 0, where this first derivative is 0, we will be able to tell what the original function is doing by figuring out the sign of the first derivative on these intervals. So if we want to know what's happening to the left of 1, we need to pick a number a little to the left of 1, say 0, and plug it in to the first derivative to see if we get something positive or negative. If we plug a 0 into the first derivative, we get 0 minus 0 plus 3. So we get something positive. If we pick a number between 1 and 3, say 2, and we plug it into the first derivative, 2 squared is 4, minus 4 times 2. 4 times 2 is 8, so 4 minus 8 is negative 4, plus 3 is going to give me negative 1. So between 1 and 3, my first derivative is negative. And then finally, something bigger than 3, so we can pick something like 4. So 4 squared is 16, minus 4 times 4, another 16 gives me 0, plus 3 is something positive. So this gives me the intervals where my first derivative is positive and negative, which tells me where my original function is increasing and decreasing. So I'm going to be increasing wherever my first derivative is positive, which was negative infinity all the way until 1. And again from 3 to positive infinity. And then my original function is going to be decreasing where my first derivative was negative, which was between 1 and 3. So those relationships still exist. Let's keep going. Compute the second derivative. So when computing the second derivative, we want to go back to the unfactored form of the first derivative and use our power rule again. So the derivative here, the first term is x squared, so the derivative of that is going to be 2x to the 1. The derivative of minus 4x is minus 4, and the derivative of 3 is 0 because 3 is a constant. So the second derivative here is 2x minus 4. Part E, find the values of x for which the second derivative equals 0. So if we take our second derivative and we set it equal to 0, this is a linear function, so we don't need to factor it. We can bring the 4 over. We get 2x equals 4. So we find that x equals 2. So x equals 2 is what's going to make the second derivative equal to 0. Part F says, for which values of x is f of x concave up and concave down? So again, what we can do is we can look at what's happening around 2, because we know at 2, the second derivative is 0. So we likely are changing whether it's positive or negative. So we want to test something a little to the left of 2, say 1. If we plug a 1 into the second derivative, that's negative. We also want to test something a little to the right. If we plug a 3 into the second derivative, that's going to give you positive 2. So that means that to the left of 2, our second derivative is negative. If your second derivative is negative, that tells you that the original function is concave down. To the right of 2, our second derivative is positive. If your second derivative is positive, that tells you that the original function is concave up. So we're going to say f of x is concave up, right, when we're positive. So from 2 to infinity. And we're going to be concave down whenever the second derivative is negative, which is negative infinity until 2. Now, again, we said that at the point where the second derivative equals 0, we are likely going to have what's called an inflection point. So that's the point where we change concavity. So we're changing from concave down to concave up, because we start off concave down on the left side of the graph and we're concave up on the right side. So again, we can use our formulas in conjunction with all the things we knew before to talk about these types of things.